Hello, this is Kyung-Hwan Lee, the first author of Structure-Aware and Adaptive Representation, Learning for Continual Knowledge Graph Embedding. I'm from Big-Data Lab in Inha University, and it is a joint work with Professor Do-Won Choi. Okay, let's get started. The presentation will proceed in the following order. The knowledge graph embedding refers to mapping graph structure data, as illustrated here, into a vector space representation. In recent years, knowledge graph embeddings have found application in areas including recommender systems and question-answer generation. At the same time, they are required to be updated in real time. Therefore, the importance of continuously performing this process is being emphasized. As shown in this figure, it is about continuously generating embedding for an ever-growing graph. This is challenging because even with the same graph, the embedding representation can vary depending on the augmented scenario. This figure illustrates that even when sharing the same initial graph structure, the embedding representation of an entity can change depending on how the graph is subsequently expanded. And in this page, I will introduce a few essential expressions for understanding my presentation. A knowledge graph is represented in a smallest unit called triple, consisted of head, relation, and tail, where the relation expresses the connection between head and tail. And we will also use the symbol question mark, which denotes the group of all possible entities that can replace either the head or the tail. Here is the example of the triple. I live in Incheon, and if I replace the head I to the question mark, it means that every people living in Incheon. From now on, we will call the entities that can replace the head as a head group, and those that can replace the tail as a tail group. And let's go to the related work. In the early stages, many studies focused on applying traditional continual learning techniques. Later, more effective methodologies were proposed, but they came with additional training overhead. Therefore, the need of the techniques that can efficiently perform embedding while maintaining a certain level of performance became evident. Recently, this has been achieved in a study called CKGE. This is the basic framework of the study. This figure represents the continuous growth of graph over time. At each point, newly appearing entities are identified and sorted according to a specific criteria that divided it into n equal size groups based on the sorted order. The entities in each groups are trained using LoRa dimensional decomposition technique, with the decomposition dimensions allocated differently according to the importance of each group. But we find the two limitations of this study, and the first one was in the determining the importance of the entities. In this study, the importance was judged based on distance and degree, but changing the order of this criteria or removing one made a very little difference. So we concluded that these criteria alone are not sufficient to represent the true importance of entities. The second limitation is that the loss function is too simple. The existing loss function only regulates the relative score difference between positive and negative samples, lacking direct constraints on the actual correct answers, showing insufficient adaptability to graph with the diverse and evolving structures. Therefore, we proposed a new methodology to overcome these two limitations. First, we introduced a SMP score, which is an importance evolution metric that can reflect the structural characteristics of the graph. Our SMP score is based on the PageRank algorithm, which is characterized by the importance of each page spreading throughout the structure via links. In the most basic page length algorithms, it propagates the score to each page equally to the linked page, as shown in this figure. But the importance of each link may be not the same. For example, if the two links connected to page A are evaluated with importance to 0.7 and 0.3 respectively. In this situation, the page A with the score of 100 can propagate 70 and 30 to each links by the importance of the links. This kind of page length algorithm are called weighted page length algorithm, and also we also adopted this weighted page length algorithm, and we choose the weight as a betweenness centrality. Betweenness centrality calculates how frequently each entity or relation appears in the shortest path of the whole graph, thereby identifying whether the elements plays a key role in the overall structure. By combining these two structure indicators, we aim to measure the importance of entities more effectively. And second, we propose the adaptive loss function called ATL. We added direct constraint from the correct answer, which was missing in the existing loss function. The constraint on the correct answer is assigned inversely proportional to the square root of the size of the tail group for each triple. To understand the reason, we need to discuss the scoring function we use in this study. In our research, we employed the trans-E function, which ensures that the embedding position of the tail becomes close to sum of the head and the relation. Therefore, entities belonging in the same triple group at same tail group, which shares the same head and relations, all converge to the same correct point. However, we consider that clustering too many entities at the same point could risk collapsing the entire embedding representation. So, as illustrated in this figure, the larger groups receive weaker regularization, while smaller groups are subjected to stronger regularization. And we also added the coefficient that reflects the augment from form of the graph. This coefficient is proportional to the number of triples added to the current graph and inversely proportional to the number of entities. The reason for the inverse relation to the entities is that the rapid increase in entities poses a risk of destabilizing the overall representation. So thus the overall loss function can be expressed as follows. And let's go to experimental setup. We use 5 datasets, and each dataset result in same final graphs differs only in the way augmentation is applied. For the evaluation metrics, we adopted mean with reciprocal rank MRR and hit at n, which was same in the prior present in this session. The hit at n measures the proportion of cases where the correct answer appears within top n predicts made by the model. For the baselines, we include both traditional continual learning approach and recent CKGE methods. We will now present 4 sets of experimental results. First, the link prediction result. In most datasets, our methodology achieves the best performance. And the next is the evaluation study. As we proposed the 2 methods, SMP and ATL, we did evaluation study of these 2 components. And we can see that it is always best when the both of our suggesting methods, SMP and ATL components, are included. And this is experiments where the ATL loss function was replaced into other methods. ATL not only achieved the best performance, but the other method actually performs even worse than applying the basic trans E function, as you can see in here vanilla trans E. And this shows that ATL is very powerful in the continual knowledge graph embedding environment. And we also compare the training efficiency. Here we conduct a comparison with the fast KGE, since this method was overwhelmingly superior to other in terms of efficiency. For a fair comparison, we prepare multiple checkpoints that allow both methods to be trained for the same amount of time. As a result, we can see that our methodology achieves better performance across all datasets and the average checkpoints. And lastly, we show the embedding space analysis. Here, for many-to-many relation triples, we visualize the distribution of head groups and tail groups by applying t-SNE for two-dimensional reduction. In all examples and across all groups, our methodology shows more compact clustering. Not only, in addition to the qualitative comparison, we also conducted the quantitative evaluation. Using our RMS metric, we measure the variance per dimension of original embedding without dimensionally reduction. In these cases, also our methodologies applies the embedding or found to more tightly clustered. And finally, the conclusion. We propose the continual graph embedding methodology that is structurally aware, efficient, and effective, and validate it through the multiple experiments. Thank you for listening my presentation, and this is the end of my presentation.
Thank you very much for the presentation. So I'm just having a look at the Q&A questions. So I don't see any questions. So I will proceed. So this was very interesting. So I have a couple of questions. So the first one is whether your method would be applicable to any other knowledge graph embedding beyond trans E.
Yeah, because our method is not belong to the specific embedding method, it can be adapted to other embedding methods, not only trans E.
Okay, and so that's why I thought. So I have a second question. So now, if you compare, for example, your method with fast KGE, because the underlying technique is the same. But
Yeah.
now you have more information, more fine-grained information to know. So how much actually representation you need to allocate. I was wondering. So did you compare so the embeddings? So for example, the dimension sizes that you got with your method with respect to fast KGE. So is there a substantial difference in the resources that they will allocate to the different entities? Did you compute that difference? Could it be that, for example, for some entities now your method will use, for example, more dimensions that fast KGE for instance?
Can you speak your question again?
Yeah, I will. So my question was whether you inspected the resulting embeddings, so using your method on fast KGE, and did you see substantial difference in the size of the embeddings, for instance?
The size of embedding?
Yeah.
You're meaning the how many dimensions?
Exactly.
We give the same embedding size with fast KGE.
But this is for the initial knowledge graph. But then when you go continual, you may allocate different sizes, right, to the new entities. Is it right or not? Or perhaps it's me who didn't understand. Yeah.
We gave the same dimensions
Mm-hmm.
when the graph goes bigger.
Okay. So it's always the same dimension.
Okay.
All right. Okay, so we don't have much time, so I thank you again for your presentation, for your answers. So let's move to the next talk. So